Okay, your video is about examining growth and decay, specifically with exponentials, or that's what we're going to be continuing, is our work with exponentials, specifically with growth and decay. So you remember that B is the growth and decay. It tells whether it's growth or decay. If it's growth, then it's greater than 1. And if it's decay, then it's less than 1. So that would be 1/2, 3/4, 0.2, anything like that. Over here it will be 2, 3.1, 4.9, anything like that. Okay, it might also be 1.02, something like that. Barely over 1, but that's still a growth function. Okay, it's an exponential function. In an exponential function, the number that is underneath the exponent represents the growth factor. So we're going to talk about this word right here, growth factor, and knowing that whatever is right underneath the x, that's the growth factor. Okay, that's what we call the growth factor. All right, so let's talk about the following problem. So let's look at these two examples. Okay, so the very first thing you want to tell is what is it, growth or decay. This one is clearly growth because that number is greater than 1. So it's growth, and then it asks us for the growth or decay factor, and for this problem the growth or decay factor is 1.45. Okay, so we'd say 1.45, but then it asks us what the rate of growth or decay is. This one was growth, and this is growth again, so kind of only need to answer that once. But the rate of growth, okay, the rate of growth, if you remember the formula that we did in class, it was this. It was A equals P times 1 plus or minus R to the T power. And that this one right here was the rate. Okay? So if you think about this, if this was 1 plus 0.45, then in this case, the rate would be 45%. Okay, 45%. So for this problem, we're going to say 45%. Okay, the growth rate is 45%, because this is what that number would have been. Okay, if we would have had an original formula like this. Okay, and then evaluate for x equals 8. So I'm literally going to plug this in and plug 8 in for x and see what we get out. Okay, when we do that, we get out 468.98. Okay, 468.98. Okay, next example, example number 2. Same thing, is it growth or decay? This one is decay because it's less than 1. So each one of these will be decay. None of them will be growth. And the growth, the decay factor here is 0.78, right? And now we want to find the rate of growth. And so I'm again referring back to this formula, 1, and its decay, so it will be this right here. We would have to think, what is that going to be? What is that R going to be? So for this problem, that would be 1 minus 0.22. 1 minus 0.22. And so we say the rate of decay would be 22%. 22% for that problem. Okay? And then evaluate for x equals 5. So I'm going to literally plug this all in and put a 5 and then figure it out on the calculator. So we get 2.31 will be the answer for this one. And notice that it did go down. The original amount, the initial amount or original was 8, and it went to 2.3, so it decayed. Okay, real important that it decayed. And then if you notice up above that it grew, it went from 24 all the way to 468. So it grew quite a lot in that problem. Okay, so and then let's do the next two examples. So example number 3 is this, and this is a little bit different. It says the number of mosquitoes at your summer camp has tripled every year since 2005. In 2005, there were 3,000 mosquitoes. write a model for this situation. So here's some important numbers. 2005, 3,000, tripled every year. That's real important, okay? So it's a growth factor. They're asking us a growth equation. So I'm going to use the equation, this equation here, okay? And I'm going to plug into what I need to. I know that the original amount of mosquitoes is 3,000, so I'm going to put 3,000 here. Now this is different. Right here, what I want you to look at is that this spot, whatever's underneath, represents the growth factor. Growth factor, okay? So I want you to think for a second about what the growth factor is going to be, and it's going to be this number triple, okay? So in here, I'm just going to put a 3. I'm not going to put 1 plus anything. I just know that when it tells me a number like tripled or doubled, I can just put that number here in the middle, okay? And then for T, it says from 2005 to 2015, and in that time, it's a 10-year period. 10-year period, so I'm going to use a 10 right here, okay? And then I'm going to just solve that out and see what I get. And I get that there's a whole lot of mosquitoes. So how many is that? 177 million mosquitoes. That's a lot of mosquitoes over a 10-year period. But if they're tripling every year, that does make sense, okay? All right. Next one is example number 4. Your dad bought a new truck for $24,000, but the value is depreciating at a rate of 15% every year. So we're going to use this formula: A equals P1 minus R to the T. Now, this problem gives us a percentage of rate, so I'm actually going to plug that in. It would be 1 minus 0.15, and the principal or the beginning amount is $24,000, and the T is the time in years is 7 years. It's asking us how much is it going to be after 7 years. And so I'm going to put all this in a calculator and figure this out. It would be, and the way I figured it would be $7,693.85. And you should try to get these in your calculator and make sure that I'm doing them right, but also make sure that you know how to do each one. Okay? And then lastly is half-life problems. So when we talk about half-life, I want you to take a second and write this down, but the half-life is a science term, and you probably refer to this in science at times, but this is the most important function here. A equals P times 0.5 to the T. What I want you to notice is that T doesn't necessarily represent the time in years like it used to. Now it represents the number of half-lives in a given time period, okay? So that's a little bit different, okay? So our first example here is talking about fluorine, and fluorine-20 has a half-life of 11 seconds. Half-life of 11 seconds. Find the amount of fluorine-20 left from a 40-gram sample after 44 seconds, okay? So the very first thing, the first step that we're going to do is find T. Find a number of half-lives in a given period. So T is going to be different. We're going to have to find it for this problem, and what we do to find it is divide the time period by the half-life. So the time period that it gives us is 44 seconds, and the half-life is 11 seconds. And both those come from the problem. It says 11 seconds is the half-life, and that it's 44 seconds. So we do that, we get 4 is the time period. The value of T is 4. And so when we do the function here, it's going to tell us we're going to put 40 in. That was the amount, the grams in the problem. We're going to put 4 in right there. That's a 4 if you can't read it. And then we work that out, we get 2.5. So there are going to be 2.5 grams of fluorine remaining after 44 seconds. Okay? So that's just an example of a half-life problem that we're going to do. We won't do many of them, but I wanted you to see it one time so you know and understand what it is. So make sure you watch this video and take good notes on it. Go back and watch it again if you have to.